Dear students, in this video I am going to discuss numerical problems which appeared in the year March 2016. Let's have a look on the very first problem. That is, in Young's double slit experiment, fringes of certain width are produced on the screen kept at a certain distance from the slits. When the screen is moved away from the slits by 0.1 meter, fringe width increases by 6 into 10 raised to minus 5 meter. The separation between the slits is 1 millimeter. Calculate the wavelength of the light used. In this problem, we can see two situations. The first one is before going to move the screen away from the slits, we will get a certain fringe width. And after moving the screen away from the slits by 0.1 meter, the fringe width increases by 6 into 10 raised to minus 5 meter. And separation between the slits is constant in both the situations, that is 1 millimeter. We need to calculate the wavelength of the light used. So let me assume the initial distance. So how much distance we have? We are having a certain distance. Let me consider that distance as d1. When we have a distance between the screen and the slits is d1, we will be having a certain fringe width. Let me consider that one as initial fringe width. Let it be beta 1. When the distance between the screen and the slit is d1, the fringe width we are having beta 1. Now, when we move the screen away from the slits by 0.1 meter, we get the final distance, that is the final distance. When we move the screen away from the slits, let it be beta 2, and this will become d1 plus 0.1 meter. When we increase the distance like this, we'll get the fringe width 6 into 10 raised to minus 5 meter. That is, the fringe width increases by 6 into 10 to the power minus 5 meter. That is final fringe width is equals to beta 2. This can be written as beta 1 plus 6 into 10 raised to minus 5 meter, because the fringe width increases by 6 into 10 raised to minus 5 meter when we increase the distance by 0.1 meter. So we will get like this. And we have a separation between the slits, that is 1 millimeter, that is constant. Let it be small d, that is 1 mm, 1 into 10 raised to minus 3 meter. So we need to calculate the wavelength of the light used in this experiment. Okay, so as we know that the fringe width is equals to lambda d divided by d, where capital D is the distance between the slits and the screen, and small d is the separation between the slits, and lambda is the wavelength of the light, and beta is the fringe width. So let me use this formula in these two situations, that is before going to move the screen from the slits and after moving the screen from the slits. So let us see now. So in the first situation, that is before going to move the screen from the slit, let me consider this one as beta 1 equals to lambda d1 divided by d. So after moving the screen through a certain distance, that is lambda, when we increase the distance, at the time we will get a new distance, that is d2 divided by d. When the distance is d2, we will get the beta 2. So we know that the beta 2 is equals to beta 1 plus 6 into 10 raised to minus 5 meter. So this is equals to lambda into d2, that d2 equals to, as we know that, d1 plus 0.1 meter divided by small d. Now beta 1 is equals to, we know that beta 1 equals to lambda d1 divided by d plus 6 into 10 raised to minus 5. This is equals to lambda d1 divided by d plus lambda into 0.1 divided by d. And this lambda d1 divided by d and this lambda d1 divided by d will get cancelled. Now we get only 6 into 10 raised to minus 5 is equals to lambda into 0.1 divided by d. So make lambda as subject formula, we will get lambda equals to 6 into 10 raised to minus 5 into separation between the slits divided by 0.1. So this can be written as 6 divided by 0.1 is 60 into 10 raised to minus 5. And d, as we have d equals to small d equals to 1 millimeter, that is 10 to the power of minus 3. This is lambda, wavelength of the light used. Now this can be written as lambda equals to 60 into 10 raised to minus 8 meter, or else we could write 6000 into 10 raised to minus 10 meter, or we could write in terms of angstrom, that is 6000 angstrom. This is the wavelength of the light used in this experiment. Okay. So let's have a look on the next question, that is, when two capacitors are connected in series and connected across a 4 kilovolt line, the energy stored in the system is 8 joule. The same capacitors, if connected in parallel across the same line, the energy stored is 36 joule. Find the individual capacitances. So let me consider those two capacitors are C1 and C2. And here when we connect these two capacitors in series and connected across a 4 kV line, that is voltage equals to 4 kilovolt, the energy stored in the system when they are connected in series, the energy stored in the system, that is US, can be written as 8 joule. Now the same capacitors, if connected in parallel across the same line, the energy stored is 36 joule, that is energy stored U when they are connected in parallel. The energy stored in the system is 36 joule. So now we need to find out the capacitance, that is C1 and C2 we need to find out. So we know that the energy stored in the capacitor is given by the expression, that is U equals to 1 by 2 CV square of CV square. So we can write that the US can be written as US equals to 1 by 2 CS V square. So CS becomes now, that is CS when capacitors are connected in series, equals to 2 US divided by V square. Now I am substituting the given values, that is 2 and US, the energy stored in the system of two capacitors when they are connected in series, that is 8 joule divided by V square. V is 4 into 10 raised to 3 whole square, CS. Now the CS equals to, so 16 divided by 4 square, that is 16 times 10 raised to 6. So this will become CS equals to 1 into 10 to the power of minus 6 farad. This is CS. Now let me consider the parallel connection now. See, we can write UP equals to the energy stored in the system of two charges when they are connected in parallel, equals to of Cp V square. So now Cp equals to, so 2UP divided by V square. I am substituting the values, that is 2 times UP equals to 36 and V square. So just now we have seen V square equals to, that is V is 4 into 10 raised to 3 whole square. This can be written as, that is 2 into 36 divided by 16 into 10 to the power of 10 to the power of 6. So now Cp equals to, so therefore Cp can be written as 2 1 ja 2 8 ja 8 1 ja 8 4 ja 5. Okay. Cp equals to 4.5 times 10 raised to minus 6 farad. So now we got Cs and Cp. We know that Cp equals to C1 plus C2. So this can be written as Cp is nothing but C1 plus C2. So 4.5 into 10 raised to minus 6. Let me consider this is equation number 1. Now here we have Cs, that is Cs equals to 1 into 10 raised to minus 6. So this can be written as C1 C2 divided by C1 plus C2. This is equals to 1 into 10 raised to minus 6. Just now we found that C1 plus C2 equals to 4.5 into 10 raised to minus 6. So we can get C1 C2 divided by C1 plus C2 equals to 4.5 times 10 raised to minus 6. This is equals to 1 into 10 raised to minus 6. Now C1 C2 equals to 4.5 into 1, that is 4.5, 10 raised to minus 6 into 10 raised to minus 6, 10 to the power of minus 12. This is C1 C2. Now by using the formula, that is A minus B whole square, that is A minus B whole square can be written as A plus B whole square minus 4AB. By using this formula, we can write C1 C2 whole square, C1 minus C2 whole square equals to C1 plus C2 whole square minus 4 C1 C2. Now on substituting the values, that is C1 minus C2 whole square is equals to, just now we found C1 plus C2 is equals to C1 plus C2 is equals to 4.5 into 10 raised to minus 6. 4.5 into 10 raised to minus 6 whole square minus 4 into C1 into C2. C1 into C2 is 4.5 into 10 raised to minus 12. 4.5 into 10 raised to minus 12. So this is equals to 4.5 into 4.5. This is equals to 20.25 10 raised to minus 12 minus 4.5 into 4, 18 into 10 raised to minus 12. This can be written as now 20.25 minus 18, that is equals to 2.25 into 10 raised to minus 12. This is C1 minus C2 whole square. Now C1 minus C2 equals to square root of 2.25 into 10 raised to minus 12. This can be written as, that is C1 minus C2 is equals to 1.5 times 10 raised to minus 6 farad. So let me write now, this is equation number 2. Let me write this is equation number 2. See, from 1 and 2, on solving 1 and 2, that is solving equation 1 and 2, we have equation 1, that is C1 plus C2. C1 plus C2 equals to 4.5 into 10 raised to minus 6, and here C1 minus C2 is equals to 1.5 into 10 raised to minus 6. On solving these, you get C2 get cancelled, so you get 2C1. 2C1 equals to 6 into 10 raised to minus 6. So therefore C1 is equals to, C1 is equals to 3 into 10 raised to minus 6 farad. That is C1 is equals to 3 microfarad. C1 equals to 3 microfarad. That is, first capacitor is 3 microfarad. And now on substituting this value in any one of the equation, that is 1 and 2, we can get C2, that is C1. Let me write equation 2, that is C1 minus C2 is equals to 1.5 into 10 raised to minus 6. On substituting the value of C1, that is 3 into 10 raised to minus 6 minus C2 equals to 1.5 into 10 raised to minus 6. So C2 is equals to, so therefore C2 equals to 3 into 10 raised to minus 6 minus 1.5 into 10 raised to minus 6. So therefore C2 is equals to 1.5 times 10 raised to minus 6 farad. That is C2 equals to 1.5 microfarad. So C1 is equals to 1 C1. So therefore our C1 equals to 3 microfarad and C2 equals to 1.5 microfarad. Okay. Let me move to the next question. Calculate the shortest and longest wavelengths of Balmer series of hydrogen atom. Given Rydberg constant 1.097 into 10 raised to 7 per meter. So here we need to find out the shortest and longest wavelength of Balmer series. We have a Balmer formula, that is Balmer formula is given by 1 by lambda equals to R of 1 by N1 square minus 1 by N2 square. And for Balmer series, N1 should be equals to 2, and for shortest wavelength, or series limit or for last line or last member of the Balmer series, we should take N2 equals to infinity. So on substituting these, we will get the shortest wavelength of the Balmer. So that is 1 by lambda shortest wavelength, that is equals to R of 1 divided by N1 square, that is 2 square, minus 1 divided by infinity square. So it will become now is 1 divided by lambda shortest R divided by 4. So lambda short, that is shortest wavelength, is equals to 4 divided by R. Here R is equals to how much? 1.09697 into 10 raised to 7. Simplifying, we get lambda short, that is shortest wavelength, is equals to 4 divided by 1.097 into 10 raised to 7, that is equals to 3.646 into 10 raised to minus 7. So this can be written as, that is equals to 3646 into 10 raised to minus 10 meter. So 10 to the power minus 10 meter is nothing but angstrom, 1 angstrom. So shortest wavelength of the Balmer series is equals to 3646 angstrom. Okay, in the same way, we can find out longest wavelength. So for longest wavelength, or for the first member of the Balmer series, N2 should be taken as 3. So on substituting, we get 1 by lambda, that is longest wavelength, is equals to R of 1 by N1 square, that is 2 square, minus 1 divided by 3 square. So on simplifying, we get the R of 1 by 4 minus 1 by 9. This is equals to, that is 5R divided by 36. Is equals to 1 divided by lambda. So now lambda or longest wavelength can be written as 36 divided by 5R. And substituting the value of Rydberg constant, that is 36 divided by 5 into 1.097 into 10 raised to 7. So now 36 divided by 5 into 1.097 is equals to 5.485 into 10 raised to 7, and this is equals to 36 divided by 5.485 is equals to 6563, that is 6.563 into 10 raised to minus 7 meter, that is longest wavelength. So this can be done as, that is longest wavelength is equals to 6563 into 10 raised to minus 10 meter. This is nothing but the longest wavelength, that is longest wavelength is equals to 6563 angstrom. Okay, this is the longest wavelength of the Balmer series. Let me move to the next question, that is calculate the resonant frequency and Q factor of a series LCR circuit containing pure inductor of inductance 4 Henry, capacitor of capacitance 27 microfarad and resistor of resistance 8.4 ohm. Here we have inductor of inductance 4 Henry, capacitor of capacitance 27 microfarad and resistor of resistance 8.4. So we need to calculate resonant frequency and quality factor. Here in the question we can find out the inductor of inductance, that is L is equals to 4 Henry and the capacitor of capacitance, that is C is equals to 27 microfarad, that is 10 to the minus 6 farad, and resistor of resistance, R is equals to 8.4 ohm. So we have an expression for the resonant frequency, that is A of R, resonant frequency is equals to 1 divided by 2 pi square root of LC. And substituting the values, that is 1 divided by 2, pi value is 3.142, root L is equals to 4 Henry and C equals to 27 into 10 raised to minus 6. So on simplifying this, we get 2 into 3.142 root 108 into 10 raised to minus 6. So this is equals to, that is resonant frequency is equals to 1 divided by 6530 into 10 raised to minus 3, and this can be, this becomes, that is a resonant frequency will be equals to now, that is resonant frequency is equals to 15.31 hertz. This is the resonant frequency of the LCR circuit. Now we need to find out quality factors. So we know that the quality factor is equals to angular resonant frequency times L divided by R. So substitute the values, will get the quality factor, that is Q is to omega R equals to 2 pi f R L divided by, and substituting the values, that is 2 into 3.142 into resonant frequency, that is 15.31, sorry, frequency equals 15.31 into L equals to 4 Henry divided by R, this is 8.40. So on simplifying, we get the Q is equals to 384.83 divided by 8.4. So we get quality factor is equals to 45.81. There is no unit for this. So we will get only 45.81 value. This is the Q factor and this is resonant frequency. So let me move to the next question, that is 3 resistors of resistances 2 ohm, 3 ohm and 4 ohm are combined in series. What is the total resistance of the combination? B. If this combination is connected to a battery of EMF 10 volt and negligible internal resistance, obtain the potential drop across each resistor. See here, let me write the given resistors are R1, R2 and R3. That is R1 is equals to 2 ohm, R2 equals to 3 ohm and R3 is equals to 4 ohm. They are connected in series. If this combination is connected to a battery of EMF, that is EMF of the battery we have, that is EMF of the battery is equals to 10 volt and negligible internal resistance, that is small r equals to 0. And we need to find out potential drop across each resistor, that is V1 we need to find out, as well as V2 we need to find out, and V3 we need to find out. So we know that whenever the resistors are connected in series, then the effective resistance is equals to sum of the individual resistance, that is the effective resistance is equals to sum of the individual resistance. So we can write Rs is equals to R1 plus R2 plus R3, that is equals to, that is 2 ohm plus 3 ohm plus 4 ohm. This gives us, that is 9 ohm, that is the effective or total resistance of the combination is 9 ohm. This is Rs. Total resistance of the combination is 9 ohm. This is the answer for the first question A. Now for B, if the combination is connected to a battery of 10 volt and negligible internal resistance, obtain the potential drop. If you want to find out the potential drop, first we need to find out the current flowing through the circuit. So the current is given by, that is current is equals to E divided by EMF of the battery or cell divided by external resistance plus internal resistance. Now on substituting the values, that we will get I, that is I is equals to EMF is equals to 10 volt and Rs, here the total resistance should be considered, that is 9 plus internal resistance is 0. So 10 divided by 9, 10 divided by 9 gives us, so I is equals to 10 divided by 9. This is equals to 1.111, that is I is equals to 1.11 ampere. Now the potential drop across each resistor, let me write the potential drop across R1 or resistor 1 is equals to, that is R1 is V1 equals to IR1. So this can be written as I is 1.11 into R1 is equals to 2. So V1 is equals to 2.22 volt. This is V1. In the same way we can find out V2, that is potential drop across R2 is equals to, R2 is V2. This V2 equals to IR2, that is V2 equals to I is equals to 1.11. There we have R2 equals to 3. So V2 is equals to, so therefore V2 is equals to 3.33 volt. This is V2. Now in the same way we can find out V3, that is potential drop across the resistance R3. So now potential drop across R3 is equals to, that is V3 is equals to IR3. So therefore V3 equals to I equals to 1.11 and R3 is equals to 4 ohm. So therefore V3 is equals to 4.44 volt. Okay, so the total resistance of the combination is 9 ohm and the potential drop across the each resistance, that is V1 equals to 2.22, V2 equals to 3.33 and V3 equals to 4.44 volt. Okay, this is the solution for this question. Okay. Thank you. Thanks for watching.